있는데
네.
알겠습니다.
네. 네. So yeah, except two guys, most are using this deep learning approach in their research, right? Okay, so we will briefly review this deep learning. As I mentioned in previous lecture, this ImageNet has been one of the sensational event in deep learning community, right? So this is very large scale data setting image classification domain. And there was challenges held every year. But in 2012, before this year, the state-of-the-art algorithms are based on the shallow learning algorithms like SVM. But in 2012, the RLXNet comes out and there have been 10% accuracy improved, okay? So after this, people are gradually interested in using the deep learning algorithms, okay? And also in 2015, the ResNet appears, and this even go beyond the human performance in image classification task, okay? So after this, people are gradually also interested in deep learning, okay? And this is some slide showing that why deep learning approach is better than the previous shallow machine learning algorithms. So in the first row, it is showing the conventional pipeline using shallow learning algorithms. Okay, so given input image, we have to define, this is the shallow learning algorithms pipeline. So given input image, we have to design our own feature vector. How to extract feature vector, we have to define by ourselves. So for example, for face recognition task, the color information, the skin color might be very useful feature to recognize the face, right? So we have to define such feature vector by ourselves in this shallow learning architecture, okay? And then the images are transformed into this kind of feature vector like skin color or texture or some other feature vector. And then you will apply the shallow learning algorithms having just one layer. Maybe you will think this as just one layer of MLP, okay? And actually this is the SVM algorithm, okay? You only learn the algorithm that have one layer, and you will input these extracted features into this machine learning algorithm, and then you will output. You learn these algorithms to output the class probability, okay? That's the way we learn image classifier in conventional machine learning algorithms, okay? So the thing is, these kind of human engineered features are not very optimal, right? So we may miss some useful information which might be very crucial for our targeted application, okay, by the mistake, okay. So anyway, this hand engineered feature is not very optimal, okay. But deep learning algorithm, it can learn every layers from the data, input and output features from the scratch, okay? So in deep learning architecture, the first part of the layers are becoming like the feature extractor. And the later part, it becomes like the classifier, similar to the conventional machine learning algorithms, okay? Anyway, these feature extractors are automatically learned from the data. So we can think this whole pipeline is more optimal than the conventional pipeline. Okay, so in the conventional pipeline, by the mistake, we can miss some of the features, right? But in this deep learning architecture, we may not make that kind of mistake. Okay, so we can say this deep learning architecture is more optimal. Okay, so this is actually the reason why deep learning architectures are better than conventional machine learning algorithms. So it can extract optimal representation via end-to-end learning, right? For machine learning algorithms, we have to design dedicated representation or feature vector by ourselves for each task, okay? For face detection task, we have to extract maybe skin color, or for other application, we have to design some of the feature vector which might be useful for that specific task, okay? But in deep learning, we don't have to do that. The deep learning architecture automatically learn intermediate representation from the data, okay? In that sense, the deep learning architecture can extract more optimal representation, okay? And the other reason why deep learning is better than shallow learning is the non-linearity, okay? If you stack multiple layers, it can kind of represent non-linear mappings between input and outputs, okay? But if you have only one layer, you can represent only the linear mapping between input and output, okay? But most of the real-world applications, including computer vision, the data are in nonlinear relationship. There are some nonlinear relationship between input and output. Okay, yeah, that's the real-world situation. So we can say deep learning algorithm performs better than conventional algorithms in real-world situation. Okay. So this is actually two reasons why deep learning performs better than the conventional shallow learning algorithms. Okay. Any questions in the middle? No? Okay. So yeah, this is the CNN algorithm, which is one of the representative deep learning algorithm. So CNN is actually the subset of deep learning algorithms. Okay, this is abbreviation for convolutional neural network. Okay, so this is one of the deep learning algorithms, and it is saying that it is using some convolution operation, right? Most people are maybe focusing on learning how this convolutional neural network is working, right? How the convolution operation, how the convolution layers are working in this CNN. But I want to say the most important thing is their differentiability, okay? Any differentiable layers could be here in between. This is the input, right? And this is the output. And any differentiable layers could be in between this input and output if they are differentiable, okay? But convolutional operation was here because it is the differentiable operation, and at the same time, it is efficient operation for processing 2D arrays, okay? So CNN, they are using convolution operation because that's good or efficient for processing 2D arrays. And at the same time, they are differentiable, okay? But I think I want to focus on this differentiability rather than the efficiency of convolution operation to process 2D arrays. Okay, any operation could be here, but and in the image processing domain or signal processing domain, the convolution operation, the 2D convolution operation was widely previously used for processing the 2D images or 2D arrays already. So they used this, okay? But I think more important condition was the operation itself was differentiable, okay? And when I say the differentiable, this means two things. When you, let's say this is the input X and this is another output Y. And when I say differentiable, it means we have to calculate dy dx. Okay, the differentiation of output Y respect to the input X. We have to calculate these things. Okay, and another important condition is maybe we can have to first define the forward path, how to get this Y from the input X. That's the function f, right? So here we define the function f having some parameter sector, okay? So h of I is here, but this is same as x, right? So the function f can map the input x to the output y using the parameter sector, okay? This is the first condition. The output should be differentiable respect to its input. And the second condition is the output could be differentiable by its parameter, okay? So we have to define these two gradients to be used for the deep learning architecture, okay? Conversely, if you have these two gradients, any layers could be between the input and output, okay? Any layers that have these two gradients could be used for constituting the deep learning layers, okay? So to be used as the one of the layers constituting the dim layers, you have to define these three rules, actually. The first rule is the forward rule, which propagate from left to right, okay? So you have to define how to obtain your output given the input X, okay? And using some parameter sector, okay? For example, you can define your output using your input and parameter sector like this, right? So you have to define this kind of forward rule, okay? And another two important thing is you also have to define these two gradients, okay? But if you define your output using some connecting some operations, then this backward rule is automatically defined, right? Let's say if your output y is defined like this, then its gradient dy dx is defined like this, right? Yeah, there's some automatic rule in mathematics, but you have to define anyway in your code. You have to define this kind of gradient, okay? If you do not use any deep learning libraries like PyTorch or TensorFlow, if you implement these deep learning architectures using only NumPy library, then you have to define this kind of gradient by yourself, okay, for each layer, okay. And also you have to define this dyd sector by yourself, okay. Then, if each layer is having this information, by the chain rule, you can obtain these two backward rule and parameter update rule for entire architecture, okay. So for example, I will get DLD sector. I want to get this DLD sector. That could be obtained by multiplying dyd sector and dldy. Okay, this is the chain rule, right? So differentiation of the last output respect to some of the intermediate parameter sector could be defined by differentiate of intermediate output respect to that parameter multiplied by differentiation of this final output respect to the intermediate output, okay? This is the chain rule, right? So if the entire deep learning architectures are composed of differentiable layers having these two gradients, then we can obtain these two backward rule and parameter update rule for the entire network, okay, by the chain rule, okay. So this is important thing, okay. Is there anybody who is not fully understanding this? In Korean, I want to summarize this. So 이 세 가지가 각각의 레이어에 정의가 돼 있으면 이 레이어들을 쌓은 전체 딥러닝 네트워크가 체인 룰에 의해서 이 세 가지 룰을 가지게 된다는 겁니다. 다 이해되나요? Okay. Anyway, then the thing we will do is this actually. So sector new, this is kind of sector old, D sector DL. Okay. So actually, the thing we want to achieve is learning the entire deep learning architecture work for our targeted application. Okay. The sector in every layers are initially randomly initialized. Okay. If our parameters are randomly initialized, when we input our input, like any image, if we input any image, then our output would be some random output, right? So it is not totally working, okay? It only outputs the random output, okay? But if we are given some data and if we update our parameters using this rule, okay? This is anyway updating the parameter sector, right? If we can update our parameter using the data, then the network is gradually working for our targeted application, okay? And actually for that purpose, what we do is defining this kind of loss function. This is measuring the distance between ground truth and our final output. Okay. So the measure frequently used for measuring this distance between our output and ground truth is the Euclidean distance. Okay. So ideally, if our output is same as ground truth, then this distance might be 0. Okay. So the distance between ground truth and output should be minimized during the training. Okay. So we will update our parameter sector in the middle to make this loss close to 0. Okay. So we will update our parameter sector to make our output close to ground truth. Okay. Right. And that L is located here, right? So this DL, this sector is meaning that how the loss L is changes according to our parameter sector. Okay. So this gradient is meaning that, right? And if we update our parameter sector to the minus direction of DLD sector, then it means this that is the direction where the loss could be minimized, loss could be reduced according to, anyway, this gradient is meaning the direction where the loss L could be reduced, okay? Scale scalar value like 0.01 or 0.001, okay? We will multiply some small scale value to this direction, and we will indeed update our parameter sector, okay? And if we do repeatedly for data, update these parameters repeatedly, then our parameters are gradually working for outputting proper output, which is close to ground truth. Okay. Okay. So anyway, the more primary condition for learning the entire network is that each layer should be differentiable. Okay, if each layer is having these two gradients, if two gradients are properly defined every layers inside the deep learning architecture, then we can do this. Okay, we can update parameters, right? Okay. That's the the primary condition. Okay, and this CNN is selected because it is differentiable operation which have these two gradient. And at the same time, it is already known in image processing domain that it is good and efficient operation for processing the 2D image. Okay, so in CNN, most of the inputs are 2D images. Okay, so people use this convolution operation to constitute the deep learning architecture to process the 2D images. Okay. Okay. And actually, this, maybe you saw this formula multiple times, right? So what they're doing is updating the parameters, okay, using this direction, okay? This direction is the direction to reduce the loss function, the distance between ground truth and output, okay? So are you guys following me? Okay. Okay. So okay. And I will show you how to calculate the gradient by the chain rule in deep learning architectures. Previously, in this shallow learning algorithm, we also use this gradient descent, okay, updating the parameters towards the direction of gradient, DL theta. But people thought that in this kind of deep learning architecture, applying this gradient descent was not easy, okay? But that's why actually, they already know taking multiple, because of this difficulty of applying gradient descent in deep learning architecture, people was afraid of constituting this kind of deep architectures, okay? Actually, this backpropagation algorithm was needed to apply gradient descent in deep learning architectures, okay? After that, people could train these deep architectures and use these deep architectures, okay? Okay, and I will conceptually show you how they could calculate gradient in deep architectures, okay? Let's say these are some variables, x, y, and z. They are input variable, and this is the output, okay? And we can say x plus y. This is the formula this graph, okay? So we connect each variable using higher to output the final output f, okay? And let's say we input -2, 5, -4 to these variables, okay? Then the final output would be -12, okay? This is kind of defining the forward loop, okay? Propagating the signals from left towards the right, okay? This is the forward loop, right? Then I will show you how to calculate this kind of deep gradients, okay? We have to calculate this kind of gradient, okay? We actually have to calculate the gradient for intermediate nodes, okay? That's actually the parameters in the middle of the deep learning architecture, okay? So we can set the final node's gradient as 1, okay? Let's assume this 1 is same as a differentiation of f with respect to itself, okay? This is 1. And then we want to calculate this df dq and df dz, okay? Which is directly connected to f, this multiplier, okay? Then we will again write down the formula here, right? And when calculating df dq, this is q. When calculating df dq, we will regard this g as constant. And now the z is -4. It is initially having -4, right? So we will regard z as the constant -4. Then we will differentiate the left and right side by q, okay? Then df dq, we will differentiate both sides respect to q. Then this is -q, so we can say this is -4, okay? We can directly obtain this from this, right? So dfdq is now -4. Okay. Are you guys following this? Okay. And also we want to get this dfdg, and for obtaining this dfdg from the same formula, we will regard this q as the constant, and it was set as 3, right? This was the formula, right? 3 multiplied by z. And then we will differentiate both sides with respect to z. And we can get this value is 3, okay? So in the red font, they wrote these values, okay? And next, we obtain these values until here. And the thing we want to obtain next is this one. Differentiation of final output f to x and y, okay? At the first step, we only calculate the node's gradient, which is directly connected to the final output. And then if they are calculated, we will see the next, okay? We get gradient here, then we can calculate gradient for the next node, which is connected to the gradient 4, okay? So here, we will first calculate this dfdx, and by the chain rule, this could be defined as like this, okay? We already calculated dfdq, which is -4, right? And then we will only calculate dq dx, okay? And we can also load the previous formula for this q. Q is x plus y, okay? X plus y is q, right? And we have to calculate this dq dx. And for obtaining this dq dx, we will regard y as the constant 5, okay? Y was initialized to 5 before, right? And we will differentiate both sides again. Then dq dx is 1, okay? So we could calculate df dx by this manner. So dq dx is 1, right? And this was -4. So the entire gradient is -4, okay? -4 is here. -4 is here, sorry. And if you do same thing for y, you can feel that dy, we also have to find this value, right? And this is samely like here, right? Using chain rule, this is again like this. And if you do same thing, then you can find this is 1 and this is -4. So the entire gradients are -4, okay? So actually in deep architectures, using these algorithms are actually called as backpropagation, okay? So using this kind of backpropagation, you can calculate all the gradient in the middle of the deep learning architecture, okay? And then you can calculate this DLD sector for all of the intermediate parameter sector, right? And you can update parameter, okay? Okay. So I think if you understand this backpropagation and these two conditions, which is required for this gradient descent, then maybe you understand how to learn this deep learning architecture. Okay. So between this input and output, any differentiable layers could be there, right? But because we are processing this 2D image, we select the convolutional operation, okay? And people constitute the architectures like this, okay? Okay. So the performance, the accuracy could be varied according to how you constitute the intermediate layers, right? The order of the convolution and dimension of the filter size, dimension of the intermediate layers, and so on, that are related to the accuracy. Okay, how your architectures are performing for your targeted application. But the thing, you can do this, you can learn over architecture. The reason behind is those layers are already differentiable. You already can find two gradients for each layers of the deep architectures, right? So you could train them architectures, okay? Okay, so today I will finish here, and after this Wednesday, we will see what is the that 2D convolution and what is the convolution layer that could be built by the convolution layers, convolution operation, and other types of layer in CNN, the pooling layer and the activation layer. Okay. 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 Anyways, sorry for delays today, and I will continue again from next class. Okay, let's finish here. Thanks a lot.